Welcome to today's deep dive. If you're joining us, you are probably exactly like me.
Insanely curious about how things actually work.
Yeah, right beneath the surface,
Yeah,
especially when it comes to the technology shaping our everyday world.
absolutely.
Today, our mission is to explore a radical paradigm shift in artificial intelligence. We are looking at a system that completely rewrites the rules of how AI accesses, organizes, and processes massive amounts of information.
And to really understand this shift, we are examining a fascinating stack of highly technical documents today.
Very technical.
Yeah, we have a comprehensive research report simply titled the Master Technical Specification.pdf. We've got an architectural design document known as the Core Blueprint.md.
Hmm.
And we even have actual Python code dumps for a system called Deterministic GraphRag.
Which is also frequently referred to in these documents as the three-manifold mind.
Right, the three-manifold mind.
I just love that name. It sounds like a concept pulled straight out of some high-concept sci-fi novel.
It really does.
But the implications for enterprise architecture are incredibly real. Here is the hook. For anyone out there who uses AI, and let's be honest, that is pretty much all of you listening, you have probably noticed that sometimes the AI just forgets things.
Or it hallucinates connections that aren't actually there at all.
Exactly. Or,
Yeah.
if you're running enterprise software and feeding it massive company manuals, you've noticed that processing huge documents gets incredibly expensive.
Incredibly fast.
Fast, yeah. Today's deep dive will reveal exactly why that happens. Spoiler alert, it is fundamentally a physics and economics problem.
Mhm.
But more importantly, we are going to explore how this cutting-edge blueprint completely bypasses that bottleneck by mathematically demoting the AI.
Yeah.
Okay, let's unpack this. Let's start with the core problem.
Right.
Standard array and its spectacular failures.
To really grasp the failure, we first have to understand the mechanics of standard retrieval-augmented generation, standard array. It relies on what we call dense vector similarity search. So when you ask the AI a question, it takes your query, translates it into a mathematical vector, and searches a database for isolated text chunks.
Chunks that are conceptually similar to the words you used.
Yes. It's essentially looking for pieces of text that share vocabulary or high-level concepts with your prompt.
But the blind spot, according to these sources anyway, is that standard RAG fundamentally ignores how data is interconnected across a broader landscape.
It does?
The documents give a perfect, highly illustrative example of this. Let's say you have a massive data set of financial records,
Okay.
and you ask a complex question about market effects. Standard ARB might successfully retrieve a chunk of text that says A correlates to B.
Right.
And it might retrieve another isolated chunk that says B correlates to C. But because it only pulls discrete chunks based on semantic similarity, it completely misses the bridging context.
The structural topology.
Exactly, the topology needed to logically deduce that A impacts C. The documents call this the causal synthesis failure.
Causal synthesis failure. It hands you the dots, but it provides absolutely zero lines connecting those dots.
Not at all.
To fix this glaring architectural blind spot, the industry aggressively adopted something called GraphRag. The core idea was to embed enterprise knowledge into a structured graph.
Where entities like people, places, or concepts are the nodes.
Yep, and the semantic relationships between them form the edges connecting everything together.
Which sounds like the perfect solution, at least on paper. You give the AI a map instead of just a pile of random pages.
What's fascinating here is that early implementations of GraphRag actually introduced a massive new vulnerability.
How so?
Well, they built the map, but then they used the large language model, the LLM itself, as the engine to walk this graph.
Ah.
In these systems, often known as graph chain of thought, the model is fed a node and then prompted to guess which logical edge it should explore next to find the answer.
And that creates a catastrophic computational bottleneck in what is known as the LLM's key value cache.
The KV cache, yeah.
I want to spend some time on this KV cache
Mhm.
because the blueprint makes it incredibly clear that this is the absolute heart of the entire problem. You mentioned earlier that KV cache gets overwhelmed. What does that actually look like in practice for a standard enterprise model?
Think of the KV cache as the AI's short-term working memory during a specific chat session. During the autoregressive generation phase, when the AI is actually decoding and predicting the next words to output, it has to constantly pay attention to all previously processed tokens.
Just to maintain the context of the conversation.
Exactly. But recomputing the complex mathematical attention matrices for every historical token at every single step, would take way too long.
It would make real-time interaction impossible.
Totally impossible. So to speed things up, inference engines cache the key and value tensors of those historical tokens directly in a physical memory of the GPU.
Let me try an analogy here to ground this for everyone. Think of the KV cache like a chef's physical prep table in a busy kitchen.
Okay, I like that.
If you keep adding new ingredients, or in the AI's case, new tokens of context, eventually that table is completely full. You literally have no more physical space to put the carrots or the onions.
That's a perfect way to visualize it. And the memory tax required for that prep table scales aggressively. The math provided in the source documents is genuinely staggering.
Let's hear the numbers.
If you have a 128,000 token prompt running on a 70 billion parameter model like Llama 3.170b, it uses approximately 40 gigabytes of high bandwidth memory.
40 gigabytes.
40 gigabytes of HBM just to maintain that KV cache.
That is an enormous footprint for a single query.
It is.
And remember, having an LLM probabilistically walk a graph means it evaluates a node, generates a paragraph of reasoning about where to go next, and requests new data. Every single one of those iterative reasoning steps expands the context window.
It continuously appends the previous reasoning trace and the new node data to the prompt.
Because the AI relies entirely on that physical KV cache, this probabilistic walking forces the cache to expand continuously until the chef's table is overflowing.
Which leads directly to what the documents call an economic catastrophe. A single multi-hop query using commercial frontier models can cost upward of $3.
$3 for one query. When I read that in the source material, I actually paused.
It's wild.
If you were building a tool for a casual user, maybe they only ask one question a day. But at an enterprise scale, you can't have 10,000 employees running $3 queries all day long to parse through HR documents or IT logs.
No.
That would bankrupt the department by lunch.
It is economically unviable. But beyond the cost, it actively degrades the reliability of the system.
Right, because of the memory limit.
Exactly. When that KV cache eventually exceeds the physical limits of the GPU's memory, when the prep table is full, the system has to make a choice. It either has to aggressively evict older tokens, causing massive latency spikes if it suddenly needs to reference them later, or it has to artificially truncate the prompt. And when you truncate a prompt in a graph traversal, you frequently shear off the most critical structural context.
The AI's reasoning chain just collapses.
It drops the context entirely, and the AI hallucinates an answer to cover up the gap.
Which brings us to the core paradigm shift of this whole deep dive. The solution revealed in these blueprints isn't to brute force the problem by building bigger GPUs or faster hardware.
Not at all.
It's a complete architectural bypass. We have to demote the LLM. We take it from being a pathfinding engine that actively hunts for information, and we reduce it to a pure synthesis engine.
Yes.
All the reasoning, all the searching, and all the graph traversing is moved to deterministic mathematical algorithms running in standard CPU RAM.
You isolate the complex graph traversal entirely from the probabilistic nature of the LLM.
But wait, if we are completely taking the LLM out of the driver's seat and just using math to find documents, aren't we just going backward to old-school keyword search engines? What makes this different?
Because an old-school search engine still doesn't understand topological structure or semantic intent. What this blueprint does is replace the AI's guesswork with verified, mathematically constrained graph algorithms.
Algorithms that understand both the meaning of the text and the causal connections between the documents.
Exactly.
So what does this all mean? It means we build what the blueprint calls a three-manifold mind. Let's walk through these three minds, starting with mind one.
Mind one is defined as the external manifold. This is the persistent data layer, and it is organized into highly modular, swappable components called cartridges. First, you have the Content Information Store, or CIS, which uses a standard SQLite database. This holds the exact, verbatim text chunks.
It provides verifiable exactness, so you always have the original source document.
Right. Then you have a FAI index. FAIS is a library developed for efficient similarity search, and it handles all the vector embeddings.
And crucially, the specification notes that it uses the inner product on L2 normalized vectors.
Yes, which mathematically equates to exact cosine similarity without the heavy computational overhead.
Sire.
Very. Finally, you have Network X, which manages two distinct graphs, an undirected knowledge graph to map semantic relationships, and a directed acyclic graph, which maps the structural lineage and provenance of where the data came from.
Okay, so Mind 1 holds all our data.
Yeah.
It is the vast library of everything the system knows. But if I ask a question, we obviously can't scan millions of interconnected nodes instantly.
Yeah, you can't.
How does the system narrow it down without crashing the server? The sources call this the static graph fallacy, right?
Precisely. Running complex mathematical algorithms over millions of nodes for every single user query introduces prohibitive latency. It's fundamentally too slow for a chat interface.
Right.
Instead, the architecture moves to Mind 2, the session manifold. Mind 2 builds a temporary session seam. Think of it as a highly localized miniature RAM graph built exclusively for the lifespan of a single user query.
And building this localized map happens in two distinct stages. In stage 1, the FAISS index does a rapid vector search to find the top K semantic anchors.
It basically finds the handful of text chunks that most closely match the vocabulary of your query.
But then, stage 2 is where the graph topology comes into play. Network X takes those initial anchors and builds an ego graph. It expands outward from those anchors using a breadth-first search algorithm up to a predefined hop depth.
If we connect this to the bigger picture, what the system is doing is creating a highly localized, mathematically tractable boundary.
It ignores the millions of irrelevant nodes in the broader database.
Exactly. It only pulls the data immediately surrounding your specific anchors into standard CPU RAM. This focused computational boundary allows the heuristic algorithms to execute in microseconds instead of minutes.
Here's where it gets really interesting, because once we have that temporary session seam built in RAM, we have to rank the data inside it. We have to decide what actually gets sent to the LLM for the final answer.
This happens in Mind 3.
The virtual manifold. This is where the computational magic happens, and the blueprint details 3 highly specific structural tweaks to make it work. Let's start with tweak 1, min-max normalization.
Min-max normalization is a mathematical solution to a very tricky structural conflict. Within your localized session seam, you have 2 fundamentally distinct signals telling you what is important.
Okay.
You have the semantic score, which is your cosine similarity, basically how conceptually relevant the text is to the user's query. Those scores typically cluster between 0.3 and 0.9.
Makes sense.
But you also have structural density, which uses the PageRank algorithm to determine the topological importance of a node.
PageRank, like what Google originally used to figure out which web pages to show you first.
Yes, the exact same underlying logic. It measures transitive influence. A node is deemed important if other important nodes heavily link to it.
Right.
But here is the mathematical challenge the engineers ran into. PageRank outputs a probability distribution where all the scores in the entire graph must sum to exactly 1.0. So if your session seam contains 500 nodes, the average PageRank score is going to be a tiny fraction, something like 0.002.
Oh, I see the problem. So if you just lazily add those 2 metrics together, a cosine similarity score of 0.82 completely dwarfs a PageRank score of 0.004.
The math is totally skewed.
It is mathematically invalid to combine them directly.
The larger semantic scores would completely overpower the structural scores, blinding the system to the structural connections. You'd be right back to naive vector search, and you'd fail the multi-hop reasoning tasks all over again.
That's why they implement min-max normalization.
Exactly. It independently rescales the entire array of PageRank scores and the array of cosine similarity scores, so they both fit proportionally on a strict 0 to 1 scale.
The single most structurally central node gets a 1.0.
Yep.
The single most semantically relevant node gets a 1.0. It makes the 2 totally different metrics perfectly equitable.
Which perfectly sets up structural tweak 2.
The heuristic gravity scoring function. Once these scores are on the same 0 to 1 playing field, the system fuses them together using a surprisingly simple formula. Gravity V equals alpha times S plus beta times T.
To translate that out of textbook math, they are essentially creating a gravity score. It is a mathematical tug of war.
You have a dial for semantic match, which is beta, and a dial for structural importance, which is alpha.
And you blend them to figure out a node's literal attractive force to your query.
And what makes this incredibly powerful for enterprise applications is that alpha and beta are tunable.
Tunable dials.
If you are a corporate lawyer and your query is, what is the exact penalty clause in contract 4B, you want exact conceptual matches. You don't care about the broader structure of the company.
So you turn up the beta dial for semantic bias.
But if you are an IT engineer investigating a cascading server failure, You turn up the alpha dial for structural bias. You want the system to prioritize high-degree nodes and structural bottlenecks.
So you get the complete causal chain of why the server crashed, rather than just pulling a dozen isolated error logs that happen to share the same keywords.
I love the idea of just tweaking dials based on your profession.
Yeah.
And doing this math for thousands of nodes sounds like it would introduce that latency we were trying to avoid earlier, but it doesn't.
It doesn't, no.
The documents specify that they execute this using vectorized NumPy arrays. Because NumPy allocates contiguous blocks of memory and uses C-level backends, it totally bypasses Python's native loop limits.
The observable latency for ranking the entire subgraph is effectively O of 1.
Which means regardless of minor size variations, it is near instantaneous.
But even with perfectly calculated gravity scores and lightning-fast execution, we still have to physically get this data into the LLM. Which brings us to the final and perhaps most critical architectural fix.
Structural tweak 3.
Token-constrained max heap extraction.
Now, if I'm understanding the blueprints correctly, this is where standard systems fail so hard. A naive system sorts the nodes by their fancy new score and just grabs the top 50 nodes to send to the AI. Why doesn't that work?
Because LLMs do not have node limits, they have strict token limits.
Right.
A node is just a container of information. One node might be a tiny 10-word metadata tag. Another node might be a massive 500-word document chunk. If you blindly pull 50 nodes, you might only use 1,500 tokens.
Completely underutilizing your expensive context window.
Or, conversely, you might pull 50 nodes that happen to be incredibly dense, totaling 25,000 tokens.
Exactly that. And if that massive payload exceeds your prompt limit, the inference engine simply silently truncates the payload.
It chops off the end.
And truncation is catastrophic in GraphRag. It usually shears off the tail end of the causal reasoning chain.
Yeah.
You literally sever the very structural links you built the entire graph to discover.
When the AI doesn't have the end of the logical path, it hallucinates or just says, I don't have enough information.
So the brilliant fix here is combining a max heap priority queue algorithm with tick token.
Which handles byte pair encoding tokenization.
Rather than just pulling a flat number of nodes, the system mathematically inverts the gravity scores to build a max heap. This means the absolute highest priority nodes sit right at the top of the pile.
The algorithm greedily pops the highest priority node, retrieves the exact text, counts the exact number of tokens using tick token, and checks the available budget.
If it fits, it packs it in. It's like playing high-stakes Tetris with your data.
And crucially, if it encounters a highly ranked node that is just too massive and would breach the remaining token limit, the algorithm doesn't fail.
It simply bypasses that specific node and continues popping down the heap.
It meticulously packs smaller, highly relevant nodes into the remaining token margin until the budget is perfectly efficiently saturated.
It mathematically guarantees that you never breach the token limit, meaning you never suffer from silent truncation.
The elegance of that is just incredible.
It's entirely predictable. And the enterprise impact of all this, it is massive. And we know it works because the proof is actually in the code dump provided in our sources.
This isn't just a theoretical white paper full of academic wishes.
This is a fully functional Python desktop app running locally. The source code clearly shows it running using Llama, which proves that this entire architecture requires 0 cloud APIs and 0 external vector databases.
You can run it entirely, privately, on your own machine.
The efficiency statistics provided in the evaluation metrics are genuinely mind-blowing.
By offloading all this complex topological reasoning to the deterministic Python layer and relying on that max heap extraction, the actual number of tokens sent to the LLM is reduced by up to 89.3%.
89.3%. You are only sending the absolute highest value verified data.
And because the context assembly in standard RAM takes fewer than 50 milliseconds before the LLM even sees a single word of it, the end-to-end inference latency is slashed by over 90%.
You aren't forcing an expensive GPU to hold massive, redundant graph-walking tensors.
And for me, the absolute biggest win of all is eradicating hallucinations.
Generative models hallucinate logical paths because they are inherently probabilistic. They guess based on patterns.
But this new mathematical traversal acts as an unyielding physical constraint.
If a structural path does not explicitly exist within the NetworkX global topology, the mathematical algorithm physically cannot traverse it.
Therefore, that unverified data never enters the session seam.
The AI is physically incapable of hallucinating a structural connection because it can only synthesize the mathematically verified, strictly bounded data it is handed by the max heap.
The LLM is restricted strictly to final linguistic synthesis. It takes the perfect data and turns it into a human-readable sentence.
It is a fundamental paradigm shift from probabilistic searching to deterministic extraction,
It really is.
which perfectly wraps up the core lesson for you today. The future of scalable, reliable AI isn't just about throwing billions of dollars at building bigger and bigger probabilistic brains.
No.
It is about building smarter, deterministic mathematical boundaries around those brains to protect their working memory, permanently prevent hallucinations, and frankly, protect our wallets from $3 queries.
This raises an important question, one to really mull over as this technology matures.
I'm listening.
If all the heavy lifting, the complex causal reasoning, the memory management, the graph path finding can be completely offloaded to these deterministic mathematical manifolds running on a standard cheap CPU,
Right.
does the LLM itself eventually just become a commoditized translation layer?
Wow.
If the math does all the actual thinking and retrieving, could we soon swap out incredibly expensive frontier models for the absolute cheapest, smallest open source models without losing any enterprise-grade reasoning power?
Now that is a fascinating thought to leave on. If the math does the heavy thinking, the AI just does the talking. Thank you so much for joining us on this deep dive. Keep questioning how your technology actually works beneath the polished surface, and we will see you next time.